This is a continuation of the last video on variation of parameters. I am splitting up my work to solve these two integrals on either side, and I'm going to look at this one first. The reason why I'm going to be giving myself all this room to solve these integrals is I just wanted to convince you that this integral, right, is not just 1 over t. Right? I think it's certainly tempting to do this. It's not even 1 over t plus c, so that is not true. The way that I convince myself of this is that if I want to take the integral of 1 over t, so a different problem. This is like t to the 1, or sorry, t to the negative 1. Power rule tells us that we need to add 1 to that, so we get sort of a t to the 0 situation. This relationship here, this is the actual integral. So this one is more complicated than that. So we can't do that. I'll actually start with this one. This is a integration by parts problem. So I'm going to start off by saying u should be something that when we take the derivative of it, it becomes easier and it becomes simplified, and dv is something that we know how to integrate. So this u is going to be my natural log of t, dv is going to be dt, du is equal to 1 over t dt, and v is just going to be equal to t. So when I write out my equation, uv minus integral of v du, I get u times v is going to be t times natural log of t minus the integral of v du, and that works out very nicely. So we get t times natural log of t minus the integral of 1, which is just going to be t. So I'll leave it at that for now, and then I'll do this other one. Like I said, not a u substitution, and we're going to need to do integration by parts. And there's not immediately a really great choice for there's not immediately a great choice for dv here. I'm going to call this t, or sorry, I'm going to call this natural log of t, and this is going to be 1 over t dt. But there's not a great choice for dv here, but we're just going to have to trust that the process will work for this. Right, this isn't something that gets easier when we integrate it, but it will help us simplify things. So this is 1/2 t squared. That means that this piece is going to be equal to uv so it looks something like that, minus the integral of v, so we'll put the 1/2 out here, du, and we see that it does cancel out nicely, so one of those t's can be removed. I'm going to say it's 1/2 times this whole thing, natural log of t times t squared, minus 1/2 is already taken care of over there. Integral of t is going to be 1/2 t squared. We could simplify this even further, I think I'll do that before I plug it back into the equation. So this is 1/2 t squared or rather, I'll say t squared. Yeah, I'll take that. And this one I'm going to call t times natural log of t minus 1. Okay. Plugging these back into our particular solution, where y of p is equal to negative y1, then integral of this thing here. So we just did this integral over here. That's going to be, I suppose I can skip this step. So this is negative y1, which is e to the t, times t squared times 1/2 natural log of t minus 1/4 plus t e to the t times t times ln of t minus 1. The reason I simplified it beforehand was because now I can, the reason I simplified that before was now I can write this as t squared e to the t times this whole thing. So negative this so it'll become a plus 1/4 plus natural log of t minus 1. Right. So I will end up with the particular solution is going to be equal to t squared e to the t times, let's see, have positive 1/2 natural log of t, and then minus 3/4. I think the problem is done. If you're not asked to simplify your solution, I think the problem is done here at this step, but this is the a much nicer form to look at, and I bet if you were actually going to use this to solve for some values, maybe you needed to find C1 and C2, this would be a much easier form to look at. Okay. So that's it for the particular solution. I'm going to say that our general solution is this, and rather than write out the complementary solution and the particular solution here, I'm just going to use a trick to say I've already defined yc and yp in this problem, so I'll say as they're defined above. I also accept just the phrase as above. If you've already defined them, you don't have to rewrite them. Okay. The last thing that I wanted to do, now that we've actually solved this problem, is tell you a little bit about where we get that long equation, negative y1, integral, Wronskian, all that. So where that comes from is we're setting up a system of equations here. And this is the system of equations that we set up. But the idea is that our complementary solution looks like this. C1y1 plus C2y2. And so the thought with this method is, what if we take our particular solution and instead of calling it C1y1 and C2y2, what if we have some functions, u1 and u2? u1 and u2 are functions. And that way, we're going to be able to figure out some way to have particular solutions that aren't, they're just not going to be constants, right? And they'll be independent from the complementary solution, and they'll also solve the differential equation. So the way that we do that, or the way that we connect this idea to this set of this system of equations, is we have two restrictions. So we're going to have two formulas and two restrictions that we can impose. One of them that we impose is that yp has to solve the differential equation. And the second one, this is sort of a free restriction that we get to choose. So the choice that we make in order to make the system of equations easy to work with is that y1 u1 prime plus y2 u2 prime is equal to 0. The result of that, if you want more information on that, let me see, the page in your textbook is section 3.9, page 169 for a more in-depth explanation of why this works, but for now we get the system of equations y1 u1 prime plus y2 u2 prime is equal to 0. And the second one looks like this, where everything has a prime in front of it. That is, we're taking the derivative of it. We can use the system of equations. So just like in the particular solution, y1 and y2 come from the complementary solution. But we can solve for u1 prime and u2 prime from this. And it turns out that u1 prime is going to be equal to, if you solve this system, then you're going to get that u1 prime is equal to negative natural log of t. And that u2 prime is going to be equal to t times natural log of t. We want the particular solution to look like this. This is y1 or u1 times y1. So if you compare these, well, if you need u1 from u1 prime, you need to take its integral. So you get the particular solution is going to be equal to y1 times the integral of negative natural log of t dt plus y2 times the integral of t times the natural log of t in this example. Okay? But more generally, we find out that this is always going to be y2 times g of t divided by the Wronskian. This is always going to be y1 times g divided by the Wronskian. So if you compare this to what we saw in when we just kind of set up this formula, and started writing it was that the only difference is this negative sign gets pulled out in front, and then it'll look identical to what we figured out just by solving for the Wronskian, putting G of t and y1 and y2 in the right spots. So, so I'll say this will produce the exact formula we saw earlier. I'm showing you this for a couple reasons. One is I wanted to give you a little bit of a sense that I'm not just getting this equation from nowhere. But the other reason is there may be a situation, I could certainly think of one where solving this system of equations to find what goes in front of those integrals would be slightly easier than solving for the Wronskian. Maybe there's a difficult Wronskian to solve for, but yeah, I think for the most part, most of the time I want you to sort of derive everything and really know the mechanics behind everything. But for this particular topic, I think just knowing the formula, and I'll show you the form. So this is a good form for memorizing it. But I think that very first form that I drew, where is it? Yeah, that very first form that I drew, this is the one that I think you should refer to when you're doing these problems. Okay. So that's it. Hopefully this video, I think I solved the problem with the video glitching out. So I'll keep uploading these. And yeah, let me know if you run into any issues. Thanks. Bye.